Golden star to the right shines in the night.
Hi! So in this problem, part A, we are asked to find the second derivative of the given differential equation. Pretty simple. So the first thing we do is we're going to take the derivative of that first term x squared. So using just, the power rule, it becomes 2x. And then for the second one, it becomes 1/2, and the derivative of y is 1, but we need to include that dy dx because it's given to us in terms of dx. So we don't want to just leave it in terms of dy over dx. We want to leave it in x and y. But we do have the original dy over dx that was given to us, so we can just plug that in where we had the dy dx in our previous step. So once you plug that in and distribute your 1/2 out, you're going to end up with the second derivative, which is 2x minus 1/2 x squared plus 1/4 y. And just finishing it up on screen. Yay! Okay, so in part B, we are asked to decide whether there is a max, a minimum, both relative, or neither at the point -2, 8. So in order to do this, we want to look at two things. We want to look at the first and second derivative so that we can look at the slope and concavity respectively. So the first thing we're going to do is look at that first derivative to get the slope. All we're going to do is plug in -2 for x and 8 for y into our original dy over dx equation that was given to us. And you're going to see that is equal to 0, meaning there's a slope of 0 or the tangential line at that point is horizontal. So now that we know the slope, we want to look at the concavity. To do that, we have to employ our second derivative, which we already found in part A. And just like before, we're going to plug in -2 and 8 into our x and y spots in the equation to find out what the concavity is. If it's positive, we're going to be concave up, and if it's a negative value, it's going to be concave down at that given point. So once we plug in the points, just do some simple arithmetic and a little bit of algebra, we are going to see that it's, drum roll, this is going to be a long drum roll because I write very slowly so you can see very clearly, it is -4. So now that we know it is concave down, we can put that and our slope together. So if the slope is 0 or it's horizontal, and we have something that's concave down, I'll draw it better than I acted out with my hands in just a second. We're going to have something that looks kind of like a hill, or something that has a relative maximum at the point -2, 8. So based on the horizontal slope and the downward concavity, we can conclude that there is in fact a relative maximum at the point -2, 8.
I'll make a man out of you.
In part C, we are given g of x, which is a particular solution to the differential equation given, and it contains the point -1, 2. So we're asked to find the limit as x approaches -1 of g of x minus 2 over 3 times x plus 1 squared. So the first thing we want to do is just plug in -1. So we get g of -1 is 2, minus 2 gives us 0 in the top, and we also get 0 in the bottom when we plug in -1 for x. So when we have 0 over 0, we know that's an indeterminate form, and my mind immediately goes to using L'Hopital. So we want to take the derivative of the top and the bottom. So the derivative of the top is going to end up being g prime of x, and the bottom is going to be 6 times x plus 1. So all we did again was just take the derivative of the top and the bottom individually. So now that we know we need to use g prime of x, we want to figure out g prime of -1 because we're going to try and plug in -1 again to see if we can find a limit. So we know that the function g of x is a particular solution to that initial differential equation, so we can use that differential equation given to find the slope. So all we're doing is plugging in -1 and 2 to the x and y values given in that original equation. And once we've plugged -1 back in, we are going to get g prime of -1 equals 0 over 6 times 0. So we're back again at 0 over 0, our indeterminate form. So we're just going to keep on chugging along and find now the second derivative of g of x, because we're going to find the second derivative of the top and the second derivative of the bottom. Lucky for us, we actually already found the second derivative of the specific differential equation in, I believe it was part A. So just like we did one step above, we're going to plug in -1 to the differential equation we have for ourselves. And finally, we get -2. So now we can plug in g prime of -1, which is -2, over the derivative of 6 times x plus 1, which is simply 6, to get -1/3. So -1/3 is the limit as x approaches -1.
Yes, you'll be in my heart from the
So in part D, we are given our last function that is a particular solution to the differential equation given, called h of x. And given that h of 0 equals 2, we are asked to use Euler's method to approximate h of 1 using 2 equal step sizes. So the first thing I did, just to help myself, was write out the formula for finding the first term using Euler's method, and I also wrote down some basic information to help organize my thoughts. Y naught equals 2, x naught equals 0, h, our step size, equals 1/2, and the derivative or differential equation equals x squared minus 1/2 y. So first thing we want to do is find y1. So all we're going to do is plug in that beautiful information that we wrote down for ourselves. So 2 plus, and then we're just going to plug in x naught and y naught values, which are 0 and 2, into that beautiful differential equation, and h as 1/2. Okay, so finally we found that y1 equals 3/2. So now we know that y1 equals 3/2, or h of 1/2 is approximately 3/2. We can find what y2 or h of 1 approximately equals. So we're just going to repeat what we did for the previous step, except whenever we see a naught, we're going to plug in a 1, and whenever we see a 1, we're going to plug in a 2. Those are for all the little subscripts. So all we're going to do is plug in our x1 and our y1 into the equation that we've written for ourselves. Do some more boring number crunching. And finally, we're going to find that y2 equals 5/4. So in other words, the approximation of h1 using Euler's method with those 2 equal step sizes is going to be 5/4. Ta-da!